Hey students, let's go through exam number 2 here. All right, let's begin here. It says here, the terminals of a battery with an EMF of 1.58, and so kind of this Duracell battery we did in class, and an internal resistance of 0.25 is connected with a 22 gauge nichrome wire. And so if you remember in lab, we used a lot of 22 gauge nichrome wire, and then this is its diameter. When the nichrome wire is first connected, there is a current of 1.86 amps. Then, of course, it'll warm up. After a time, the nichrome wire warms to a new higher temperature, so the resistance will go up, and then the current will drop to this value. All right, so A, and if I kind of start here with Ohm's law, and maybe kind of turn this into a circuit diagram, I would have my EMF, I would have some internal resistance, and then I'll just make the resistance that corresponds to the wire. So maybe I'll call this R sub I for internal and R sub W for the wire. And so looking at this, you can see we're in series, and so the equivalent resistance is the internal plus the wire. And that equivalent resistance would be the voltage divided by the current. So in this case, 1.58, and when we first turn it on, 1.86. And so grabbing a calculator, 1.58 divided by 1.86 has an overall equivalent resistance of 0.849. And so that means the wire, because the internal is 0.25, and so minus 0.25, gives me a 0.599 ohms from just the nichrome wire by itself. Okay, so then, and of course I hope you're recognizing this straight out of Chapter 27, this internal resistance is the resistivity times the length over the area, okay? And so this first question, A, says, what is the length of the nichrome wire? So if I were to take the, I'll call it the area times, oops, move this over, resistance of the wire divided by the resistivity, we'll get the length. So the area would be pi times radius squared, which I'll write as 0.321 times 10 to the minus 3 squared. And this resistance is what we just went through, okay? And then the resistivity, let's grab the textbook here and turn to the beginning of, what is this, I guess, chapter 27 here. Here's the page I'm looking for. But the resistivity of nichrome is this 1.5 times 10 to the minus 6. So 1.5 times 10 to the minus 6. And so if I put all these numbers into the calculator here, we've got pi times 0.312 times 10 to the negative 3 squared times 0.599 divided by 1.5 times 10 to the negative 6. And so this gives me a distance that is 0.129, and this would all be in meters. So pretty close to 13 centimeters here. Kind of want to round things. Okay. Now, of course, notice then the second part it warms up, and so the current drops. And so the new equivalent resistance would again be this V over I. But the V stays the same, but the I went down a little bit to 1.63. And so if I go 1.58 and divide it by 1.63, we get an overall equivalent resistance of 0.969. And like we did in part A, if we subtract off the internal resistance, we'll get a little higher. And so now the resistance of the wire is 0.719 ohms. And using the relationship that the resistance changes by this coefficient, temperature coefficient, then we have our new resistance here. And we can find, of course, this increase in temperature. So the wire's gone up to a higher resistance of 0.719. And it was, let's see, back here on A, 0.599. And we get 1 plus alpha delta T. And so if we take the resistance and divide it by what we had before, and if we also subtract 1, we're looking at about a 0.201 alpha delta T. And so now if we divide by the alpha, which again, we got to go back to the textbook or the internet here, but here's our nichrome, here was our resistivity, and here is our temperature coefficient. So 0.4 times 10 to the minus 3. So I'll just go divide by 0.4 times 10 to the negative 3. And that's going to give a change in temperature of 502 degrees Celsius. Of course, I guess we have to say change in temperature is final minus initial. Steady state temperature. Ooh. This should say it, and it doesn't. I think I will add that on here. 20 degrees C. But that was kind of implied in all of our problems when we didn't specify here. Remember, we were saying all values take for room temperature here at 20 degrees C. And so I will add that on there for the test day. And then this will become 522 degrees Celsius for the steady state temperature. All right, nice. And hopefully that one goes pretty well for you, because that was out of chapter 27, which, as you know, the chapters start to get a little harder after this. All right, let's go on to the second one then. And so the second one says this, and that's out of chapter 28 here. It says, look at both of these figures. So we have two different circuits. And like all these problems, A is hopefully pretty straightforward, and then B is going to be a little more challenging here. But in A, we're going to look at this figure. Each resistor is 10 ohms, and what is the equivalent? So hopefully right away you see that these two are in series, so that's equivalent to a 20. And then that 20 is in parallel with that 10. So if I go 1 over 10 plus 1 over 20 and take the reciprocal, that would be the equivalent of these here. And that group of 3 is in series then with the 10. And so I guess I have 10 reciprocal added to 20 reciprocal, hit enter, take the reciprocal of that. And so those 3 in the group here are equivalent to 6.66. So if you just add 10, you're looking at 16.7 ohms for the equivalent of these 4. Now, of course, The harder one here is the ones where we don't have any equivalencies. And that's why we have this very complicated circuit here. There's a node between all of them, so nothing's in series, and then there's some element between before you get from the front of one to the back of the other. So there's nothing in parallel. And so I'm going to have to just go right to the Kirchhoff's laws and solve this. And there's a little hint in here. It says, what is the current in each of the 4 resistors? And so it says, go ahead and, do the 3 loops and then the nodes. But it kind of helps you out here because why don't I call the current in the 10, current number 1, and the current in the 20, number 2, and the current in the 30, number 3, and the current in the 40, number 4. Now, of course, you can see that one splits off and goes to the battery, so we could call this like current 5 and this current 6. But as a hint's trying to say here, you might be tempted to do 6, but remember the problem's only asking for in the resistors. So we might be better off not to think of this problem as 6 unknowns, but only 4 unknowns. And so if we do 3 loops and a node that doesn't include these currents, we would only have our 4 unknowns. And so that's why the hint is here to kind of help you along and say, don't make this one harder than it needs to be. It's already hard enough. And so we'll just do our 4 equations, 4 unknowns. And actually, I don't know if you see it coming, but number 1 is going to be almost too easy to solve. So I'd really say this boils down to 3 equations and 3 unknowns, current 2, 3, and 4. Now, by the way, I just labeled the directions of the current, and as I explained in class, I like to give an educated guess of which way they flow, but sometimes you don't really know, and so you just set it up there and then try to solve. And if it comes out negative, then it was opposite of what you thought. So that's what I'm going to do. And I'm pretty confident because the 5 is bigger than the 1.5 that 1 goes this way and 4 goes this way. What I'm not real confident about is number 2 because this 5 could be strong enough to push then this way. I suppose, though, that this 1.5 is strong enough to push because this 5 gets weakened a little bit by a 10. But see, it's only a small 10, so I don't think it's going to get weakened enough. So that being said, probably my educated guess should put the current the other way. But I'm just going to stick to that and see where it goes. Not real sure about number 2, but very confident with 1 and 4 and 3. All right, so let's do the first loop here. Maybe I'll start in this corner and go plus 5 from here to here, minus 10, I1, minus 1.5, and that completes the first loop. And this is what I was saying, that when I look at this loop, there's only going to be current number 1, and that's easy to solve for. I mean, if I go 5 and minus 1.5, I get 3.5. And if I bring the 10 I1 to the other side, I eventually just get I1 as 3.5. So I guess I could just put 3.5 in units of amps right away here for the current, I forgot to move it, 0.35. When we move it over. So there is current number 1. And that's why I said really then these other ones are coupled because see the 20 shares a top loop and a bottom loop. And that's going to have the equation with it 2 in each of these, and so they'll be coupled together. And so the other ones won't be quite so simple to do. And in fact, let's do this lower right-hand loop. Maybe I'll start here and go plus 1.5 minus 20 I2 minus 30i3, and that completes the loop. You might want to write this as the constants on one side and the variables on the other. Maybe I'll put a little box around it to remind me. I think this is going to be one of three important equations to find out these three unknowns I still have, number 2, number 3, and number 4. Now, if I do this top loop, maybe I'll start here and go clockwise. This would be a minus 40i4. And as I go around, I'd go against the current, so plus 20i2. And against the current there, so plus 10i1. And that completes the loop. Oh, and remember, I1 is 0.35. So this is actually then 3.5. And so why don't I move these to the other side? So this becomes minus 20i2 and plus 40i4. That would be a second equation involving those three unknowns. And then, as the hint said here, go ahead and look at this node here where the 20, the 40, and the 30 all combine. But it looks like the 2 and the 4 flow in. So 2 plus 4 has to equal what flows out, which is current number 3. Which, again, I guess we could write as I2 minus I3 plus I4 equals 0. And so these three equations have the three unknowns that I'd like to solve. And, excuse me. And so maybe I'll go ahead and write this as a matrix, and I'll put current 2, current 3, and current 4. And so if I look at this first one, there would be a 20 times current 2, 30 times current 3, nothing times current 4, and that equals 1.5. And this equation here would be a negative 20, a 0i3, and a 40i4, and that equals 3.5. And then this last one would have a 1, a negative 1, and a 1, and that equals then 0. And so if we let the calculator do all the math for us, we should be able to solve this. And so let me go here to matrix A. There is my matrix. Here we go. Oh, let me put this in the screen. Looks like it's kind of messed up here. All right. Well, let's see. Matrix. So let's go matrix. And let's go edit. And maybe I'll just do something a little different. Usually I use matrix A, but I've been doing some work, so I want to save matrix A. So let me go to matrix B. And let me give it a 3 by 4. And so let me come down here then and put in a 20, enter, 30, enter, 0, enter, 1.5, enter. Okay, down here, negative 20, enter, 0, enter, 40, enter, and 3.5, enter. And then 1, enter, -1, enter, 1, enter, and 0. And maybe just to double check, let's see, that column works out. Let's double check this, 0, 4, okay. Let's double check this one, 30, 0, -1, and 30, -20, and a 1. All right, so then I'll just go quit. So matrix B, in my case, is the one I want. So now if I go to matrix and I want to do some mathematics, okay, let's do the reduced row echelon form, okay, of matrix B. So I'll select matrix B. And then this will manipulate it and come up with a current. There's the negative. And so I get a negative 0.0173, I guess I'll do that here for number 2. And so keep in mind then current 2 is really going that way. Number 3 is 0.0615. And equation number 4 is 0.0788. So maybe I'll put those in the box, 0.788 here, 0.0615 here, and negative 0.0173 here. Yay. Now, it might be worth kind of just checking this. I guess during an exam, you might not because you don't have too much time. But this should really say, with 2 going the other way, that what's coming out is 2 and 3 in magnitude, and that should equal 4. And so if you add these together here, and so that 1 and that 6 makes a 7, that's good, and that 7 and that 1 make an 8, and okay, and then 2 and 3, ignoring the minus sign, does equal number 4. So that checks out. Maybe a couple of other things is, if you kind of look at this loop here, with the current coming in right here, remember the current's really going the other way, there would be a drop here and a drop here. That would have to be the same as the drop here. So if I take the current at number 3, which is 0.0615, and I multiply it by 30, this is a drop of 1.8. If I go this direction, which would be 20, and again, I'll just think of this as absolute value because I'm going to go this way. This current's really going the other way. So 20 times 0.0173 is a drop. And then another drop due to the battery. That should be the same drop. Yeah, so this loop makes sense. Maybe I should have just gone all the way around the loop and showed it equal to 0. And kind of the same thing here. If you start here, you're going to drop this here, which we mentioned earlier would be the 3.5. So this should be 3.5. So that means the drop here plus the drop here should be 3.5 to get to the same place. So 40 times the current in number 4, 0.0788, and the 20 times the current in number 2 in terms of absolute value should also be the same drop, 3.5. Yeah, and very, very close. So feeling comfortable that that is the correct set of numbers here. And so I'll call that good and say, all right, well, let's go on to number 3. Another circuits one, and again from chapter 28, and kind of a hard one. It's got 3 parts. I'll start with A, but it's got a switch, it's got some capacitors and a battery and some resistors. It says, look at the circuit, the capacitors are uncharged. So the key to this one, it says when the switch is first closed, we could think of a circuit when it's first closed, so the switch is closed, as if the capacitors or a closed switch. So this is the circuit that's in my mind. And as I look at this, the current would go through the 1000 and split and go through the 2000 and the 3000. And so the 2000 and the 3000 are in parallel. And so the equivalent of those would be 2000 reciprocal plus 3000 reciprocal, inner reciprocal. And so we're looking at about 1200 for the equivalent of those two. And of course, it should be smaller than the smallest one. And then that result was really in series with the 1000. So that's why the whole circuit has an equivalency of 2200. So the current coming out of this battery would be the voltage divided by this equivalent resistance of 2200. So we've got 9 volts divided by 2200. And so 9 divided by 2200 is, and I'll do it in milli, 4.09 milliamps. Now, technically, that's what's coming out of the battery, but given that the problem was hard in itself, I tried to make it simple. Let's see, where does it go? The current in the 1000, yeah. So all of it comes out of the battery and goes to the 1000. So what we just solved for was not only the current coming out of the battery, but also going through the 1000 before it splits off. And so we don't have to go any farther in A and do any kind of current dividing on here. This is what comes out of the battery. This is what goes through the 1000. And that's good because, like I said, there's enough to this problem as it is. But I hope you kind of caught that was one of our lessons, that the switch can be thought of as a closed wire, if you will. And then the reverse is true later on, that once it's been closed for a long period of time, you can think of a capacitor as being an open circuit. In other words, the capacitors fill up and you don't get any results out of it, nor any current flowing through it. And so with that being the case, we can just say, all right, I'm just going to ignore that resistor. And so really what you just have is these two in series, the 1000 and the 3000. So that means your equivalent resistance is just 4,000 ohms. Okay, and so we've got 9 divided by 4,000. And in milli would be 2.25 milliamps. And so that's what would be coming out of the battery. But because they're in series, it would be what's also flowing through the 1000 and the 3000. And again, the problem was a little nice to us. We don't have to split it off. Well, I guess there is no splitting off for this one. Anyways, but whether the question said coming out of the battery or going through the 1000 or the 3000, it would be that same number. And then, of course, the real challenging one of this, part C, is then now that the switches has been closed for a long time, now that the capacitors have filled up, and now that you open the switch, hopefully you kind of see that the 1000 ohm resistor and the 9 volt battery are kind of out of the picture. They've been disconnected by opening that switch. And so now this is going to discharge. And of course, again, a little bit harder is we've got two capacitors, but we would have the equivalent of those two. And then they would be discharging through two resistors that are in series. Of course, we'd have the equivalent of that. And since those two resistors are in series, I'm just going to add these two. So it's discharging through the equivalent of a 5,000 ohm resistor. A little bit of calculator work is going to be required here because we have capacitors in series, and that's where you have to do the reciprocal sum. So I have to go 1 reciprocal plus 2 reciprocal, enter reciprocal of that. And of course, this should be smaller than the smallest, and it is. And so this is 0.667 microfarads for the equivalent capacitance. And so just kind of seeing that may take a while and a little bit of thought to say, okay, what is this equivalent to? And of course, in this chapter 28, we did this. We solved a discharging capacitor. And so now we're ready to talk about a single capacitor, which is the equivalent of these two, and a single resistor, which is equivalent of these two, as it discharges. And we learned this, that we learned that the current would be the initial current and then would decay away according to time constant tau, which is the RC time constant. And so let's figure out these two values, one being what's the time constant of this circuit, and the other what is the initial current. Because this says after the switch has been closed for a long time, the switch is reopened. What is the current in the 2000? So this one. And then, of course, 2000 and the 3000 would be the same, and so would each of the capacitors. What is the current in the 2000 resistor when the switch has been opened for 3 milliseconds? So our time constant is this equivalent resistance, 5,000, times this equivalent capacitance. So 5,000 times 0.66666 times 10 to the negative 6. And so it looks like about 3.33 milliseconds. 3.33 milliseconds. Okay, so there's our time constant. And so this 3 milliseconds is a little bit under one time constant. Okay. Now, the other thing might be what is the initial current. And so that initial current really would be the initial voltage that these two that are in series are charged up to. And we can just think about this equivalent one. And then it would be running through or pushing through these two, which is equivalent to 5,000. And this is going to take a little bit of thought and effort. And to really kind of go back to part B, remember part B, if we kind of draw this in, these two capacitors, which I'm now thinking of as one, built up enough charge to stop it from flowing, and that meant the voltage along this path and the voltage along the capacitor are the same, right? Because you go around the loop, you got to get 0, which is why it might be tempting, but wrong, to put a 9 volts in this spot. But see, it's going to be 9 volts minus a little bit. And I guess there's two ways of getting there. We could do the 9 volts minus whatever this was, which would be the resistance, 1,000 times the current, which is 0.00225. And so that's a 6.75. Or maybe even a little easier is just to say, okay, well, what is the voltage of this resistor? because that would be the same as this branch. And the reason there's no voltage drop for the 2000 in part B is because there's no current here. So whatever the voltage drop of this one resistor would be the same as that capacitor. So that's kind of a nice way. And I think even easier, let's just make sure I get the same number. So I should get 3,000 ohms times the current of 0.00225. Yeah. And so that's an important and maybe easily overlooked step here in this hard part of C, where we're now discharging our capacitor. Because like I said, you might just say, oh, it goes all the way up to 9, but it doesn't. This capacitor doesn't build up enough to stop all the current. It doesn't build up to 9 volts. It just does enough to stop this branch, which is just this voltage here. Okay, so if I take that voltage and divide it by the 5,000, that's going to give me the initial current, which I will write as 1.35 milliamps, that we have for the discharge. And so now we can put in our numbers. 1.35 milliamps for the initial current during the discharge. And this would be 3 milliseconds over a time constant of 3.33 milliseconds. And maybe I'll do this time constant first, because if I go -3 and divide it by 3.3333, shouldn't that be 9/10? Yeah. And so -9/10. And so if I go E to that last answer, I get about 41%. And so it's going to be about 41% of the 1.35. And so 0.549 milliamps would be the current at this 3 milliseconds as it's discharging. And that's a tough one. Hope you did well on that, but don't beat yourself up if you did. That's a hard one. And I have a feeling you probably got a significant amount of partial credit, discharging, especially if all you did was put a 9 there. I mean, there's a lot of other things, and so just kind of overlooking that is not a major point loss, but hopefully you learn if you're watching the video and you go, oh, I shouldn't have done that. All right, well, I think that's the last of our circuits ones. Yeah, now we get into our magnetism here. Our magnetism, you might remember, we did a long discussion on the motion of a charged particle in a magnetic field. And that's what this one's about. In fact, maybe I'll jump over to our first chapter on magnetism, because this has some nice pieces that maybe I'll grab here out of the book. But it's really kind of in this section here, which says, what is the motion of a charged particle in a magnetic field? And one of the things we, spent quite a bit of time on talking about this picture here was, okay, it's going to make a circle. And it goes through some math from your Physics 121, as well as the new magnetic force, and it gets the radius. And so since it's open book, you could just grab that formula. But I think I'll kind of derive it. Here's the new piece, that force is equal to Q V cross B. And then, of course, we would get something like QVB and the sine of the angle between V and B. Now, I must admit, your first discussion right here is they made it simpler, and they didn't have an electron, first of all. They had a proton, but other than that, it would just circle the other way. But they did set it up perpendicular, but it was a little later on where, next page over here, where they say, okay, now what if it was not exactly perpendicular, Then they said you're going to get this helix pattern, where you could then break apart the velocity of this charged particle into how much is along the direction of the field and how much is perpendicular. And in fact, that's kind of what this last sentence says. Equations 3 and 5 still can apply. You just need to replace v by its perpendicular component. And so that's what I'm ultimately going to do. We'll also need this one here, but we'll derive it too here in just a second. But this is that equation 5. So I think for this one, we really need these two equations. We need this equation 3 for the radius of it, and we're going to need this equation 5 a little bit later on to get the pitch. And hopefully you recognize this because you had a homework problem just like this. And let me give it a try. And so that's why I'm going to put here v perpendicular b equals to mv perpendicular squared. This is our Physics 121. This is our new stuff. One of the v perpendicular cancels off. And that's how we get the mv perpendicular over qb for the radius. In fact, maybe I should read the problem to you. I really haven't read the whole thing here. It says, an electron is traveling at this speed along the positive x-axis in a uniform field of this strength. And they give kind of a little grid here showing the magnetic field and then the velocity. And then they say that the magnetic field is 35 degrees up from the x-axis. So the velocity is along the x-axis and the magnetic field is angled up at 35 degrees. And it's in the xy plane, so there's no z component. The resulting motion is a helix, and so it kind of looks this. It's a helix with its axis in the direction of the magnetic field, and so this electron is going to spiral kind of along the magnetic field. That's what this whole discussion is. It looks like in the book they put the field along the x1 and then the velocity a little bit off of that. But other than switching the axes of x-axis is along which motion, this is this same problem with the perpendicular piece here. Okay, so solving for the radius, and that's what it says. What is the radius of this helix? I can just put in the mass. Let me just do it on my calculator. And so the mass of an electron is 9.11 times 10 to the negative 31. Oh, hang on. Yes. Now, maybe before I start putting things in, maybe I better take a moment and write out, okay, how much of the velocity is perpendicular to the field? And for that matter, how much is parallel? So the angle here between them is 35 degrees. And so if you were to draw your velocity vector as being made up of how much is parallel and how much is perpendicular, there would be this 35. So I can get the parallel part by taking its speed, 6.25 times 10 to the 6th, and go cosine of 35. And I get the perpendicular part by going 6.25 times 10 to the 6th and go sine of 35 degrees. And I'm going to need those numbers. So V perpendicular is, V parallel is. Okay, so let me just make sure I'm in degrees mode. Let me take the 625 and multiply it by sine of 35. So the perpendicular speed is 3.58, and of course times 10 to the 6th. And the parallel piece would be the 6.25 times cosine of 35. And so this would be 5.12 times 10 to the 6th. Okay. So probably we should do that first, since obviously you can see here that that's an important part of this whole discussion, that we need to be focusing on the helix part, the circular part, as being how much is perpendicular. Okay, so I have that number. All right, now let me come back to what I started to calculate here. All right, so the mass is 9.11 times 10 to the negative 31. And the perpendicular speed is the 3.58 times 10 to the 6th. Divide by the charge, 1.602 times 10 to the negative 19. And divide by the strength of the magnetic field here, 0.00324. And I will get then a radius of 0.00628 meters for the answer in A. What is the radius of this helix pattern? Okay. Now, B is, of course, what we call the pitch. And that might be a new word. Well, new maybe this semester, but like I said, we did a homework problem that says basically the pitch is that, how far, but as it spirals, what's the distance from one spiral to the next? And so the distance between the loop is called the pitch. Okay. So if I come over here and say, all right, I'm going to then get that distance. Remembering distance is velocity times time. I'm going to end up using this equation twice, because if I'm saying how much does it travel in the direction of the field, then I guess I want to know the velocity. That is along the direction of the field. That's what we're calling the parallel piece. That's why I said we're going to need to know this. We're going to know how it's moving along the direction of the field. And again, as we talked about in class, that's because only the perpendicular part experiences any kind of force, and the other part just travels unaffected. And that's what's going to happen while it's making its circle. It's going to be traveling along the field unaffected, and it will be going with this. Where's the parallel? This right here, this parallel speed. And let me put a capital T, taking you back, I guess, to Physics 121 for the time for one, cycle, one period, one revolution. And so this right here is what I'd like to know. This is the pitch. And I do have this parallel velocity. What I don't really have yet is the time for one cycle. But again, if we apply this same equation for what you might call the circumference, if you will, this would be the perpendicular speed. And then the time for one cycle would then represent the circumference. In other words, the period, the time for one cycle, is 2 pi r divided by this perpendicular speed. And that's what we touched on early in this discussion here. It's where this problem came from. Your author calls it equation number 5, and that's what he said, right here. Equation 3, which we already used, and equation 5 are still valid as long as you do the perpendicular component. And so that's why I have that perpendicular component. So this will help me figure out how much time it takes for one cycle. All right, so let me put this in my calculator. I already have the radius. So if I multiply it by 2 and by pi, I got the circumference. And if I divide it by the perpendicular speed of 3.58 times 10 to the 6th, I will see that it takes only 1.10 times 10 to the minus 8 seconds to make a complete cycle. That's the period of it. All right, so now I can get the pitch. So coming back over here to do the pitch, the velocity parallel is 5.12 times 10 to the 6th. Then I'm going to multiply by this time of 1.10 times 10 to the minus 8 seconds. And that's already in my calculator, so I'll go times 5.12 times 10 to the 6th. And it looks like it would travel about 5 centimeters. Yeah, 5 centimeters. Let me do an extra 6.4 here. But 0.0564 meters would then be the pitch. Nice. I like it. Okay. Another pretty tough one, but hopefully you're doing well and at least have the general idea for a lot of partial credit here. All right, and then on to the last one, which I think you can recognize right out of Chapter 30, Section 1. In fact, Part A in this picture is an exact copy of the homework, because B is pretty hard. And so I thought I'd make A kind of straightforward here, but we have a long wire, carries a current, shown in the figure, has a circular loop. And so A simply says, what is the magnitude of the magnetic field at the center of the loop? So right here at the center of the loop, we could think of this as 3 pieces, if you will, a wire that is semi-infinite long up to here, then a loop, and then another semi-infinite. In fact, if we put the 2 semi-infinites together, we get an infinite wire. So I'm going to think of this as the magnetic field created by 2 geometric figures, a long straight wire. So let me call that ST for long straight wire. And the other one for a loop, let me call it LP for a loop. I don't know if I need to turn over to Chapter 30, but these were our 2 basic figures, if you will. Here's where your author, an example, I guess, number 1 here, does this long wire and eventually gets this point here that says, okay, this is the magnetic field from a really long wire, and A is the distance away from the wire. And hopefully don't confuse that with his example number 3, where he does the ring. And he does the ring in general. Let's come back to that for Part B, where it gets harder. But he does do the special case at the center of the ring, and those are the 2 we need. And here, A means the radius of the ring. But as you probably recognized on the homework, the A, which is the radius of the ring, is also the distance away from the wire. So at least for Part A, when we write the straight wire and go mu naught I over 2 pi A, and for the loop at the center, if we write mu I over 2A, these A's become one and the same. And in fact, these equations are almost the same, as you can see. This one just has an extra pi down below. So you might even save yourself some calculator work by recognizing that. And so up here, when you go 4 pi times 10 to the negative 7 times a current of 2.35 divided by a 2 and divided by A, the radius of the ring. Now they give me a diameter. So maybe I'll put here radius is 0.6 centimeters. So when I divide it, I'm going to put it to meters, 0.006. I get a number of 2.46 times 10 to the minus 4 for the magnetic field for that ring. And if you didn't catch this during the lecture, we're going to keep going with this after the exam. But to make a strong magnetic field, when you loop it, you get stronger fields. And you see that in the math right here, because the straight wire is almost the same, but lower by a factor of pi. So if I were just to divide this answer we just got by pi, I would get the equation for the field. And that's why we make our solenoids and toroids, which we started in the lecture, but wasn't included on this exam, but will be on exam 3. We'll make things with a lot of loops. That's the learning here in terms of making it really strong. Okay, now, we're not quite done here with A, because, of course, we want to know it at the center of this loop, and they each make a field. The thing we need to be careful with when we're combining fields is what direction they are, because if they're if the same direction, it's easy, we just add them together. But if they're at 90 degrees, we got to do Pythagorean theorem, and if they're opposite, well, then we've got to subtract them. And if they're at some angle, well, then we got to do components, and it gets a little harder, and maybe even a lot harder. Now, fortunately, it doesn't happen here in A, but it does happen in B, so I thought I'd better mention it. So, but in A, if we do our right-hand rule number 2 and just kind of grab the wire with our thumb in the direction of the current, we get a field going into the screen. And if we do the loop with our fingers curled in a clockwise direction, we also get into the screen. And so these two fields are in the same direction. So it's just as simple as adding them together. And so let's see, I'll just go plus, and then I'll just scroll up to the other one, enter and equals. And so I get this 3.24 times 10 to the negative 4 Tesla as the answer to A. And so other than the numbers are different, this was, I would say it was a homework problem. I apologize. I don't think it was a homework problem. I think it was the first example I did, or second. It's like number 4 in the book. Okay. But like I said, hopefully you saw that in the lecture videos there, because this should, stand out. Like, okay. And like I said, I believe the numbers are different, but the concept of A is the same. Okay, so now here's where it can get substantially harder, because we have to think in 3 dimensions here. And now we're going to have magnetic fields that aren't in the same direction. And so when we combine them, it can get a little tricky here. Now, I'm going to use this same equation for a long straight wire. But I need to be careful with the A, because the A represents the distance away. And so here it says, what is the magnitude? Oh, by the way, notice in A it just said magnitude, didn't say direction. And I was just trying to make things a little bit easier, especially than on B, because B just says same thing, what's its magnitude. So I'm not going to worry about trying to describe the direction, although we're going to have to draw some pictures to make this sense out of this. But it says here, what is the magnitude of the magnetic field on the axis of the loop and a distance d over 2, call that radius of loop, above the screen. Okay, so we just did it right here. Now we're asked to come up right here. And so this is where I said it can get a little tricky, because I got to kind of view this in 3 dimensions. And so it's up this distance. Well, that's probably a little too much, but I want to maybe over exaggerate how far up it is. And so at the tip of the pen here, to kind of show that it's, it's along this axis. And so maybe if I use, my pen as the axis here, it's maybe up to, well, someplace up on the pen. okay? Maybe the best way to view this is not just to look at this picture, but maybe kind of picture it like this so that the current's coming at you. So if you can imagine turning the paper this way, I'll put a little circle with a dot. That would be this current right here coming at me. And so as I turn it up, I got the current coming at me. And I guess this loop that hangs down would, when I'm looking at it this way, would kind of look like this flopping down here. And this about here would be the center. And so coming above it would be right about there. And so if we continue to use the symbol A for the radius of this loop, and then we come in this picture above, and in this picture, excuse me, to the left by A, then the distance we are from the wire is square root of 2 times A. And that's the key, well, one of many keys to this puzzle, because we need to know how far away from the wire are we to calculate the strength of the field. And so I'm going to use the same equation, but now my A, the distance from the wire, is the square root of 2 times the radius of this loop. And the reason I like that is because all I really have is this same equation I did in A, but smaller by the square root of 2 because it's a little further away. And so that's going to make this kind of easy to calculate. This is just going to be 7.83. And then I'll just divide it by the square root of 2. And so this becomes 5.54 times 10 to the minus 5 Tesla for the strength of this magnetic field. Now, it'll also have a direction, but let me hold off on that for just a minute or two here. That might be, I'll add that to the picture, because let's kind of do the same logic for the loop. And for the loop, we got to go back to this more general equation that we used right here, because now the x doesn't equal 0. We're not at the center of the loop. We don't have this easy one. But fortunately, the distance along the axis, in other words, x is the A. And so this isn't going to be too bad. Let's see what we get. So the general equation is this: mu naught times I times A squared over 2. And then we have this x squared plus A squared to the 3/2. But if we recognize that this x would be in this picture this distance, how far from the center of the ring, which is A, this right here is really a 2A squared. And so this is really a 2 raised to the 3/2 power. And then this is really an A squared raised to a 3/2 power. Which, as you can hopefully see here in a second, this right here becomes A cubed, and together with this A squared just leaves a 1 over A. That's how we got this A before, and we still have this 2. And so this loop looks a lot like this equation. It just has this extra piece down here, which I'm going to write here as 2 cubed, which is 8, and then the square root. So this is the square root of 8. And so I would say that here for part B, the strength of the magnetic field from the loop is the same as we got before, but reduced by the square root of 8. So let me do that. So this would be 2.46 divided by the square root of 8. And so this is 0.870 times 10 to the minus 4. Suppose it might look better as 8.70 times 10 to the minus 5. And so that would be the strength of the magnetic field from the loop. Oh, and I guess Tesla. Okay, so that's how I would tackle this problem, is basically just do the same as I did in A. I'd get the two fields, and then just, say they're smaller by some factor. So take the result from A and just reduce it down. But like I said, now it gets a little bit harder because when I go to put the fields together, I have to ask myself, how is their alignment? Because in A, they were in the same direction, so I just added them. But they could be perpendicular. They could be opposite. They could be some angle. So let's come over here and maybe draw in this picture. And we've traditionally been doing the magnetic fields in green. So let me, continue to do that. And so as I do the magnetic field here, we learned that for the ring, it was along the axis. And so really, it hasn't changed as what we did in B, because in B, we took our right-hand rule number 2, we made a little loop here and said, okay, it was in here. And now that we're further up, it's still inward. So maybe I'll just make this long, actually I'll transfer it down here, long green line pointing inward. Well, it's pointing right on this one, because remember, this is held up. Like this. You hold it like this, the field would be going like that. Okay, so there's my field, and we might even call that the x direction. So the loop is all in the x direction. Okay. Now, here's probably the hardest part of this direction one, is here, if I kind of use my right-hand rule number 2, and I kind of imagine grabbing this wire, which is coming out towards the screen. I'll just put my little pen here. If I imagine grabbing it, it would make a field angled down like that. And so transferring it to this picture, it would look like this. And fortunately, if there's anything that makes this problem a little bit easier, is that the height above it is the same as the radius. So that's going to make this an easy 45-degree conclusion. And so we know the angle between them real easy. In fact, that's the 45 then, of course, is because it's A by A, right? This is an isosceles right triangle, which is how we got that square root of 2 times A. We knew it was the diameter of a square. Okay, so with that in mind, let me come back here then and say, okay, so the total field in the x direction is going to be the value from the loop, which is the 8.70 times 10 to the minus 5. And then the x component of the straight wire. So this would be 5.54 times cosine of 45 degrees. Whereas the y component would only have the y component of the field from this long straight wire. The loop part of it doesn't have a y component. Oh, sorry, and I forgot the times 10 to the minus 5 here. And so this y component would be this 5.54 times 10 to the negative 5, and then it would be sine of 45. And I guess it is pointing down, so if you want to call it a negative, we could and maybe should. Now, I just noticed mathematically, this is kind of nice because both the sine of 45 and cosine of 45 are the same numbers. They're 1 over the square root of 2, that 0.707. But I guess I won't worry too much about that. I'm just going to take this and go, this would be 5.54, and I'll multiply it then by sine of 45. And so this right here then is a negative 3.92 times 10 to the minus 5 Tesla for the y component. And since cosine of 45 and sine of 45 is the same, I don't need to redo this one. That's that. So I'll just take that as a positive number and add it to my 8.7, save me a little bit of calculator work. And so this will be a plus 12.6 times 10 to the minus 5 Teslas in the x direction. And so looking at this is about, 3 times bigger than the y component. Makes sense. So most of the field is in the x direction. But of course, now the last part, to get the magnitude, you got to take the x component squared and then the y component squared and then take its square root. So let me take the 12.6 and square it and add it to up here, which is the 3.93, and square it. And then finally take the square root of that. And it looks like I get a 13.2 times 10 to the minus 5 Tesla. And I suppose maybe I'll write it in a better looking scientific notation and write it as 1.32 times 10 to the 4th Tesla. So the direction here really added a twist to it. So did the extra distances. So, yeah, this could be challenging. It is challenging. So I hope you did well on B2, but hopefully you just nailed A. In fact, on all these ones, I hope you nailed A right away. The next step is a notch up, I must admit. All right. And that's it. Like I said, hope you did well. And if you didn't do so well, hopefully you learned a lot. That's probably more important. All right. Take care.